adjunct researcher at Monash University. I got that way. Originally from Adelaide, and he did his undergraduate degrees there, and Australian National University PhD, and visited, did postdocs at various places over in the US. And how long were you at University of Canterbury?
Since 1982. I won't admit that, but yeah, from 82.
Okay, so without further ado, I'd like to let Peter to start his talk on interpreting stellar spectra in the light of
Thanks, Bill, and it's good to see you all here. Oh, I can run the lights down, can't I?
Well,
yes.
Oh, you have to go. I'll let you have to go. Don't want to run them all down. Oh, more options. Oh, yeah, I can't do that. It's too many things to do. No, it's good to be here. Probably Grant knows when I was here last. Can you remember when I was here last, Grant? No. We have to look in the book. A few years ago. A few years ago. So I probably talked about spectroscopy then, I guess. But this will be a slightly different way of looking at spectroscopy. I guess Bill has given away a bit of it, saying that it's been going on for quite a while, since '82, and I guess it's still going on, and you'll see that part of my journey and the journey has evolved somewhat, and then you'll see some little things at the end. So that's what I'm going to talk about. I'm going to make this thing go forward, hopefully. So I don't have too many words, but I also don't have lots of astronomical pictures. I mainly have spectroscopic pictures, so you'll have to bear with me with that. But there are a few words here. I don't want you necessarily to remember all the words and quiz me at the end, but I guess I've always been a spectroscopist. I'm always interested in how the light gets broken up into the component colours, and then when you look carefully at that, you get pretty pictures. Like you can look at the sun, and when you look at the sun, you get the colours of the rainbow, but on top of that you get these little black stripes. And those are the little black stripes that are of interest to me, because they are elements in the atmosphere of the star, and those elements then have a certain pattern of signatures, and that signature is unique to a particular element, and then therefore you can get some of these things. You can work out what some of these things are. Now, I haven't told you what this S and R are, but there'll be a test on that. It comes up in the next slide. But so the key is to use spectroscopy, but I fully admit that photometry is quite often extremely useful as well. So we'll do it. And the other part of this thing is that you need to have some way of deducing this thing. So you can't just say, I know how much carbon there is in this star by just looking at a spectral line. You have to interpret that in some way, and the way you do that is with modelling, by modelling it with a computer model of the atmosphere, the stellar atmosphere. And it's a way of testing lots of things, testing things about how stars evolve, how the nucleosynthetic elements, how the elements have been built up, and also things on the bigger picture, so thinking about the galaxy, and I'll come the full picture when we come towards the end of the project, of the talk and the project that I'm involved in at the moment. And the key is, where do some of these elements come from? Well, you sort of know that, hydrogen and helium, and then you burn hydrogen with various things. You don't have to know about that, but basically you burn hydrogen into helium, and then you burn helium to carbon. And when you do that, there are various processes that can produce different amounts of carbon, nitrogen, oxygen in different ways. The isotopes of carbon, nitrogen, oxygen have different components as you do these through these different processes and in different types of stars. And of course, this is all happening inside stars. And when we look at stars, either photometrically or spectroscopically, we're just looking at the outer skin, the outer few percent of the star. So the question is, yes, we do see things that have been the processes of stellar evolution, where elements have been spewed out in interstellar space and elements have been then formed into new stars. But we also do see some interesting aspects of it that see that we can see stellar evolution happening in real time. And one element, and I'm not going to talk about it anymore, and it's not in my notes at all, but it just always comes to mind, technetium is one element that its most stable isotope is 100,000 years. And we see that in stars. And you might say, well, all stars are all young. But it's not because of that. It's actually because that technetium has been formed in the semi-outer layers of the star and then mixed into the outer layers of the star, and we see that. And we see it, it means that then that stuff has been formed relatively recently. So there are nice little nuances like that. So that was a few years before my time of getting involved in these things. And these things which, the R and the S process, which were on the previous slide, you know, astronomers, physicists are always, you know, a bit boring about how we do things. You know, we have R and S and it sounds very exciting. But it really is just about how you dump neutrons onto bigger nuclei. And as you dump those neutrons onto it, because you have nuclear processes that are producing neutrons, you can build up all these heavy elements, heavier than iron. Because basically, all of you people who remember your physics from a few years ago, if you think about how elements are built up, as you go from hydrogen all the way up to iron, the nuclei are getting more tightly bound. And as you go beyond the iron, they become loosely bound. So basically everything up the uranium end wants to end up at iron, and everything down the hydrogen end wants to end up at iron. And so a lot of those things, I mean, there are stable isotopes obviously beyond iron, but to get there, you have to go through these various processes here, the R and the S process. And it's really, the rapid and the slow is just in relation to them, these nuclei beta decaying. So if you dump them on very fast, the nuclei don't have time to beta decay, and so you get a whole different group of nuclei being formed compared to if you have one neutron coming on, the new nucleus being able to reconfigure with a beta decay, and then you build up a different set of nuclei going on. And so you get these interesting elements that, you know, I guess I've been looking at for a long time. We call them the light S, yttrium, strontium, zirconium, and the heavy S, lanthanum, barium, and neodymium, and also lead, which is the ultimate S process element. And then, I mean, these are only sample ones, there are many others, but europium is one of those ones where we look for the R process. And I guess I've always had an interest in the carbon, nitrogen, and oxygen as well. This is a good, for all of you who have been, there's probably a few national radio listeners in here, but there's been 2019 is the year, the 150th anniversary of the periodic table, and essentially how it was Mendeleev. I keep thinking of the former Prime Minister / President of Russia. We won't go there. We won't go there, Sergei. We won't go there, Sergei. But this picture, which has been, it's sort of popped up, and I noticed it only maybe a couple of months ago. I mean, you can see a couple of things here are interesting, which is technetium, which I just talked about, which is pink because it decays, and obviously promethium must be another one as well. Not very good with some of these. But here you can see where the different nuclear processes, the Big Bang gives you the hydrogen and the helium, cosmic ray fission gives you, or you can actually see a bit of lithium here, of course, from Big Bang. A bit of lithium up here, just a tiny bit of lithium. But you can also, you can see how the different groups of elements have been built up. And I think if you've just put in periodic table, where did I steal this from? I can't remember where I stole it from, but it's a really nice picture that gives you the whole idea of whether it's merging neutron stars that are producing some of these elements, or low mass stars that are producing some of these elements. You see that some of them are half and half, etc. But it's a really nice little diagram to amuse you in your in the nights. This is probably, for some of you, maybe a little bit more familiar, but it then puts in place where some of my research interests are. So the carbon, nitrogen, oxygen, sodium, which are sort of light elements. The light S elements, this is yttrium, zirconium here. heaviest neodymium, barium, etc. up here, and europium, and then lead somewhere up over here somewhere. And the various things, I mean, this is sort of, I mean, I guess this is what gets me excited a little bit about looking at the different elements. This is the distribution in the sun, the up and down, up and down, up and down. And so the question is then, how is it different amongst different sorts of stars? And the Lego in the top right-hand corner is something I saw in the Riken Institute in Japan, which actually shows, for some of you here might know something about the Valley of the Nuclides. This essentially is this little diagram here, sort of like a three-dimensional figure, which shows where the most stable isotopes, and the most stable isotopes are running along this valley here. Beautiful little diagram. Every day that we were there, it was a conference I went to, every day somebody would come in, because they do an experiment in their lab, and they come in and change the height of the Lego to adjust how much, what the relative, I didn't understand it, most of it was in Japanese, and it wasn't my native language. But I tend to do that because I carry various things. I carry a whole lot of $100 bills here, which are fake, of course. But I do carry a $100 bill with me because it's actually got, as well as having Rutherford, who's a graduate of the University of Canterbury, or Canterbury College as it was then, it actually has a nice little bit of science up here. It has his Nobel medal here, an image of it. But you can see a decay curve here. If you look carefully at your $100 bills, I can see you all getting your $100 bills out. I'll pass it. No, I won't pass that one around. I could pass that one around. I'll pass a fake one around a bit later. But you can actually see this, which is a decay curve. This is in days, time in days. So this is a radioactive decay curve, and this is what Rutherford called, and what is called, an activation curve. So this was one element decaying, and the other element increasing, which was the parent-daughter link in there. And so this is his work for which he got his Nobel Prize in, dare I say, chemistry, but we won't do that. I mean, the physics one was taken down. So that was in 1908. Now, this Rutherfords Den, if you've been down to Christchurch, this was the so-called old Rutherfords Den, and this was me a bit younger than I am now. So this was the old Rutherfords Den with various things in there, including this wall of medals, which currently is not in the new Rutherfords Den. Post-earthquake, a few little interesting things happened, but basically this whole building, this is in the art centre, and therefore unreinforced masonry took a while for it to get rebuilt. But this is that figure that's on the $100 bill, which is a paper from Rutherford and Soddy in 1902. And of course I noticed over here Beatrice Tinsley is on one of your things about galaxies. And indeed, she was another Canterbury graduate, not that I'm plugging Canterbury at this juncture. I'm retired from there, so I can do whatever I like. But she did her Masters and BSc and Masters at Canterbury in physics, but she did it in solid-state physics. That's what she was working on in those days. And then went to Texas and did her PhD in Texas under de Vaucouleurs, and then ended up at Yale as a full professor. And then sadly passed away at age 40 from leukemia. And so she was an amazing person. I met her once when I was in Texas. She came down from Yale, and I remember just sort of going and looking at the various papers. I mean, this is just a selection that relate to things that she did. She was a theoretician. She didn't ever go to the telescope, but she was an amazing synthesizer of the work of trying to understand things in terms of galaxies and the evolution of galaxies. And things which sort of link back to nucleosynthesis rates, the rates at which elements are built up, to understand that and how you then get the so-called metal abundance that astronomers tend to talk about, which is well, metals are everything heavier than helium for astronomers, but we're now a bit pickier than that, so we do tend to be a bit more explicit about that. But generally it's the iron peak elements that we're talking about when we talk about metal abundance. But she also worked on some things with Dave Schramm from Texas on the S-process elements, and I can't remember what the top one was, but nuclear chronology, in other words, using things like technetium to be able to realise that you can work out when certain things happen because of the fact that different elements decay in different in different ways. So that's all sort of a bit older than I am, because I'm really very young. But this was actually, I guess, my first sort of main paper, and it's from my, I guess, from my graduate work, which was on these slightly weird stars, because I guess I tended, and some of you might have heard my previous talks, have heard me talk about things, and I guess I'll mention them again, which are some even weirder stars than these ones. But this particular group of stars it's the so-called weak Gband stars. Now the Gband is one of Fraunhofer's bands. Fraunhofer noticed back in a few years ago, 18 something, he noticed that there were particular bands, and we know that you could see in the spectrum of the sun. And he named them A, B, C, D, E, F, etc. And we know some of them now as, when we talk about sodium D lines, those are lines of sodium at around 600 nanometers that Fraunhofer saw in the spectrum, and they were called the D lines. We still call them the D lines. We call calcium, singly ionized calcium, has a pair of lines in the blue, 393 and 397 or something nanometers. I know them in angstroms, but I have to be modern. But you know, those were the H and K lines. So the G band was just before that. It's around 430 nanometers. Get modern, Peter, get modern. And what John and I did was part of my thesis work. It's not going to let me go from over there. Was to model these things, to take spectra of them and then model them with what we call synthetic spectra. And I'm not going to test you on this, but you can see here, this is the so-called G-band region here. Ignore that there for now. This is the G-band region in here. And these G-band things are all molecular CH lines. So they're a carbon atom and a hydrogen atom that are bonded together, formed a molecule, and they then absorb radiation that's coming out through the sun's surface and block it out. Give those dark lines that I showed on here. In fact, if I'm very clever here, I could tell you exactly where it is. No, I'm not very clever, so I won't. Well, I can see that there's the sodium D lines, and here's H alpha. I can do that, so it's probably down 4,300. And no, I'm not going to embarrass myself. It is there in the sun. It's much stronger in these stars, which are giant stars. And so all this stuff here is absorption by the carbon and this CH molecule. And so these are sort of two normal stars, and this is a weak G-band star. You can see there's none of this stuff here in the star up here. In fact, if you're looking at those in the front, you might be able to see this dotted line here means all the CH lines in the model atmosphere have been removed. And so you can see the difference between removing them all and putting in just a few is the difference up here. This is the observed thing here. And this is 1978. It's not a digital detector. It was taken with photographic plates. Very, very different era than what we're in at the moment. This stuff over here is actually the cyanogen, a bit poisonous, CN molecule in stars, and this is the CN molecule, and this is in a normal star. This is in a weak G-band star. Weak G-band has got less CH in it, but you can see the CN band is quite strong. So what you can do is you can start working out how much carbon is down, and it's down by a factor of about 40 with respect to the sun, but nitrogen is actually enhanced by about a factor of 4. They're all in logarithmic scales. That's why I've been doing some anti-logarithms in my head. So that's what happens, is that you get these interesting interplays between the carbon and the nitrogen and the oxygen. And it's all to do with the nuclear processing that's occurring inside the star, and then that stuff's getting mixed to the outer layers, and we observe that. So I realise I'm gone to a lot of detail here. We'll go through a bit faster later on, and maybe I'll skip some as we go through as well, because otherwise I'm never going to get to all the...
May I ask, Peter?
Yes?
Which code was it? The synthesis?
The synthesis?
Well before Kourou.
No, it was Kourou. It was Kourou.
Already Kourou.
Absolutely Kourou. It was Caruso's code, because he must have done his stuff in about 1970, and I was, you know, old then.
And it's one of the first big computers.
Yeah. And a lot of this stuff was done in the time that I did it. There wasn't actually a synthetic spectrum code. All it was his model atmosphere code, and I wrote a whole lot of routines.
And punch cards.
Yeah, well, yeah, we won't go there. Yes. But I had to write a lot of routines which actually did the synthesis and actually generated all the line lists as well. So I went back to a lot of molecular physics, so I learnt a lot during my PhD about molecular physics, more than I probably wanted to know. I did play around with some things. I'm not going to talk too much about this, but basically just because it started getting interesting, playing around with synthetic spectra code and doing some weird things. And I did some things where I went to very, very metal core stars. In other words, I took out things down to down by 1,000 with respect to the sun. And what happened was that these hydride bands got very strong. So this was these hydride bands are here, and this was at a metallicity of minus, so down by 100, compared with the solar metallicity, this one here. So basically the hydride bands stayed about the same. This is magnesium hydride here. And there's some weird things happening there. It's basically because there's still plenty of hydrogen around. You can form these things with single hydrides, and it seemed as though even though all the metal lines, the iron lines and magnesium lines, got much, much weaker, these hydride bands, molecular bands, stayed strong. And I found out in hindsight that there were actually observations which had seen this, and I sort of tried to connect up the dots at one point, and then I sort of got onto some other things. So, yeah. I worked a lot on globular clusters back in the 1980s, early 80s, with people mostly at Mount Stromlo at ANU, and we did quite a lot of stuff working with carbon, nitrogen, and sodium and aluminium, which at the time seemed a bit weird. Sodium and aluminium seemed to show variations. In other words, we saw strong, between two stars which otherwise appeared identical, had strong aluminium lines. These two lines here compared to these two lines here. Subtle effects, but they were definitely significant. And in fact, when you went back and looked at the Gband, this is in angstrom, so take off a 0 and you get the nanometers. This is the Gband. What happened, there was an anti-correlation between their Gband strength and the sodium and aluminium strength. We didn't quite understand at all what was going on, and I'll tell you the punchline is that 30 years later, when I came back into this field, they were still worrying about that. And so, it's sort of now sort of understood much better, but it's very weird what's happening in globular clusters. Then I started working on what I thought were large samples, like 30 or 100 stars. Now, it's sort of a bit of a joke now, 30 years later or 40 years later, to think about working on 30 or 40 stars and thinking you have a good statistical sample. We now think we need 1 million stars to do things, and I'll tell you the story of 1 million stars a little bit later on. But this was where Chris Needham and I was, when I was in Texas, we started thinking about just observing the bits of the spectrum that you were interested in, rather than doing something like this, where you got everything and analysed everything. That you were very, very selective. You said, okay, what are the questions that we want to answer? Because it really should be. Science should be motivated by questions that you want to answer. And so we said, okay, we want to know carbon, nitrogen, oxygen, and we want to know things about the isotopic ratios. We want to know things about the overall metallicity. Titanium and iron are the iron peak elements that we were looking at. So we set about doing this. We observed in these 5 pass bands, and that's all we did for these 35 or 38 stars or something. We did 34 stars, but we had a few more standard stars that we observed as well. And we thought we did a pretty good job. And once again, 35 years later, the project that I'm involved in is to observe in very restricted pass bands to answer some of these questions, but for many more elements that we'll talk about later on. But you can get these isotopic ratios, and as I said when we were talking about carbon, nitrogen and oxygen, how the elements get changed with nuclear processing, it's actually things happen between carbon-12 and carbon-13. Because if you think what the difference is, it's the same carbon atom, it's the same atom, but it actually has an extra neutron. So what's happened is that in that nuclear processing cycle, you've ended up with an extra neutron that has been added. It's actually been a beta decay to do that, but we won't go there. But basically, you can then look at the carbon-12, carbon-13 ratio by looking at these lines of cyanogen, this time out in the infrared, rather than looking at them in the blue, which is what I was doing previously. Oh, these are the weird things that I think I probably did talk about these things, didn't I? I've talked about these things a few times. So some of the older members of the audience, not necessarily if you've been older members of the Auckland Astronomical Society will have heard me talk about this. But these are very weird stars. They're variable stars. They disappear from sight. They come back. So they're sort of anti-supernova. That they disappear and then come back. And bizarrely, as you can see the annotation along here, they have very strong lines of carbon, and most importantly, they have no hydrogen lines. This is the hydrogen line of H alpha. So this in the sun, this is this thing here. This is sort of how strong this would be. These are supergiants, but that's okay. But these are other things, and if you line up here, you see this line here actually isn't even the hydrogen line. The hydrogen line should be sort of over here somewhere. So these are something that's buried in underneath it. They almost have no hydrogen in them. And that's pretty weird, because the universe is made up of 90% hydrogen, 9% helium, and 1% everything else. These have essentially no hydrogen in them at all. Very bizarre stars. So I worked on these for a while, and we did a few things when they go into these big declines, and I mean big declines. So this is Baroni Borealis itself. So this is the prototype. So it goes from being a 6th magnitude star to being an 11th magnitude star in 20 days or something like that. So it just disappears from sight. But spectroscopically, which is what excites me, as I pointed out before, what happens is it goes from having an absorption line spectra. So this is what it looks like day minus 21 before the decline. As you go through this thing, you can see this is at the sodium D lines. These things turn into emission lines. And then this is further evolution, 100 days, 80 days, 71 days. So it just goes, it's very bizarre, extremely bizarre. And actually, has Liliana Skulin ever given a talk at the Auckland Astronomical Society? Liliana, okay. Very bizarre. There's lots of these things that we've done, lots of things I'm not going to go. But Liliana did, actually she's probably mentioned in dispatches here. Liliana lives in Auckland. Jovan, you probably remember Jovan Skulin. So Jovan and Liliana were husband and wife. Liliana did a great PhD on these things, really amazing, where she collected lots of photometry, lots of spectroscopy, put it all together, and they all do this thing. They're all incredibly bizarre. I'm not going to go into all the details, but you can see, have absorption lines here, and suddenly they're, at some later stage, they're in emission. And you have to get your head around this thing to work out, because it's all very well to get all these nice things, but then you have to actually get your head around it. And I think, I'm not even going to go there, you can see absorption lines, emission lines, huge emission lines, 1,000 kilometres per second. So there's huge, huge velocities involved. And Liliana had this lovely, lovely model that it's only a sort of cartoon type model, but basically what you have is you have the photosphere. These things do pulsate a little bit as well, sometimes not very much. But basically what's happened is that there's some sort of dust cloud obscures the photosphere of the star. So what you're then seeing, and if you think about it, if you're down here as the observer, but you can be out there if you want to swing this out, if you're looking up here and this big cloud forms in front of it, the star disappears. But if you look at it spectroscopically, what you're seeing is you're seeing scattering effects and emission from these bits, which are the chromosphere of the star. So that's what we were seeing. In here, when it goes into emission, we're looking at the chromosphere of the star, and we're looking at huge velocities, which are pressure-driven velocities, by using the force of the photons driving out the material that gives you this huge breadth in the spectral lines. And eventually it dissipates because it gets pushed out, the dust gets pushed out, and eventually it just disappears into the interstellar medium or interstar medium, and then ends up, the star comes back again. So it goes through this process. We still don't understand everything about it, but it was lovely work that Liliana did as part of the PhD. Yeah, this is a bit of a potpourri, and this is Michael Albrow and then Orland Pedersen. You probably know both of those. Worked on Cepheids. Michael started it with just looking at trying to compare, interact between stellar modelling type work and the observations. Now, this isn't a spectrum. This is, so Cepheids are stars which have periods from a few days to, depends where you want to stop them, but maybe 30, 40 days, depending on where you want to define them. But these are around about 9, 10 days, this group of stars that Michael worked on. And these are all the velocity profiles from different elements. The one here, the top left one here, is really what we call metal lines. So you look at iron, titanium, those sorts of things, and you end up getting a velocity curve which has a shape which looks something like this. Then when you look at the different elements, and this little panel here is actually now looking at deltas. So when you compare that one with iron, just iron, you get essentially a flat line. So this is mainly saying, this one up here is mainly saying it's the iron lines. When you look at, this is neutral iron, this is singly ionised iron lines, and you can see there's a bit of asymmetry going in here. So what's happening is that the different lines are forming in different parts of the atmosphere. And I guess, once again, this is the sort of thing that starts exciting me, is that what it's saying is that dynamical information inside the stars, which are being picked out by the fact that these waves are propagating out through the stars as they're doing these pulsations. And so different species respond in different ways. Here's barium-2, and this gets a bit ugly here, but what you can look at is here is, this is silicon-2, has a little dip here compared with the standard one. Silicon-1 looks pretty flat. This is calcium-1, which looks pretty flat. Calcium-2 is all over the place. And so what's happening is those calcium-2 lines are forming well out in the atmosphere compared to things here which are forming deeper in the atmosphere. So you're getting information, you're getting three-dimensional information out of the spectroscopy. So this has gone a bit further than just plotting up a spectrum. You're actually interpreting this in terms of velocity information, how the star's moving. And it gets really quite complicated.